today we will do the rest portion of the transformer, and in our last class we have studied the equivalent circuit and phasor diagram of transformer, and on the phasor diagram we have drawn for the two separate phasor diagram. One will be for resistive load, another will be for resistive inductive load and capacitive load. I told you to check in your home, and I hope all of you have checked, and it is clear from your side. Is it so?
Yes, ma'am.
Okay. Thank you for the response. Then we will check two small formula based on the equivalent circuit and what will be the equivalent resistance and reactance. So we can see clearly the equivalent circuit of the transformer, and there we can see the resistances and reactances of primary and secondary windings are R1, X1, R2 and X2. So all these are in ohms. So and transformation ratio is K. So we know this thing. Now in the secondary winding, what will be the resistive drop? It will be excuse me. So for the secondary winding, the resistive drop will be R2 into I2, and the reactive drop in the secondary winding is okay I2 into X2. Now what will be for the primary winding resistive drop? This is I1 R1 and this is I1 X1. So these are the two drops on the primary as well as in the secondary. Now if we just refer the primary side into the secondary side, we can do it with the help of the transformation ratio. So for that case we know the transformation ratio is K, and uh, if we want to transform or if we want to refer the primary side voltage to secondary, we can write this is the K times S, because we know K has a relation with I1 as well as in I2. So what is the relation? This is none other than I2 by I1. That means we can write for I2 x2 or I1 x1, we can write it is in terms of K I1 R1 and also K I1 x1. And if I is substituted is equal to K I2, if we can write this I1 will be K I2, so we can also write it will be K square I2 R1, or we can write K square I1 K square I2 X1. Now what will be the total resistive drop then in the transformer? So the total resistive drop we can write, that is we are referring to the secondary side. That means secondary will be there but primary will be in terms of secondary. Okay, so secondary is how much the total resistive drop, that is I2 R2 plus some form of primary. So primary the form is K square I2 R1. So this is the case. If we now take common I2, we will write that this is R2 plus K square R1. And what will be for the reactive drop? Again it will be I2 X2 will be same, and some form of primary will be converted to secondary, that is K square I2 X1. And again if we take common I2, we can write X2 plus K square X1. So this will be the total resistive and reactive drop in a transformer if it is referred to secondary.
ম্যাম,
Yes, বলো।
ম্যাম এটা আরেকবার বলুন না এটা।
শিওরলি শিওরলি। আচ্ছা, এটা আমি কি করছি, উই জাস্ট ওয়ান্ট টু ডু দিস এক্সপ্রেশন refer to the secondary side. We will also do it that refer to primary side. আচ্ছা, রেফার টু সেকেন্ডারি সাইড যদি আমি বলি, তাহলে আমি প্রাইমারি আর সেকেন্ডারির মধ্যে রিলেশন যে বার করব, কার রেসপেক্টে বার করব, উইথ দ্য ট্রান্সফরমেশন রেশিও। অ্যান্ড উই নো there is the relation with the voltage and number of turns at the current with the transformation ratio case. uh, so for this transformation ratio case, uh, there is a relation of the current with the transformation ratio, and if we just want to uh, mention it with the help of transformation ratio, we can write that it is k square I2 R1 and k square I2 X1, that is the primary with refer to the secondary. Okay, now what will be the total expression for refer to secondary? That means secondary resistance or secondary reactive drop will be there, but some form of primary will be considered there also. And what will be the expression? So this expression is k square I2 R1 for resistive case, and reactive case it will be k square I2 X1. So after that, if we take common I2 from these two, we can see that is R2 secondary resistance plus R1 with multiplied by k square, that is referred to the secondary. Okay, then for the reactive drop, X2 plus k square X1, that means this is the uh, resistive drop, reactive drop, that is referred to the secondary side. এরপরে this term and this term represent the equivalent resistance and reactance of the transformer, which is referred to the secondary, and this is also represented as R02 and it is referred to X02. এরপর যদি আমাদের কোশ্চেন আসে অবজেক্টিভের এই পোর্শন থেকে, শুধুমাত্র এই ফর্মুলাটা মনে রাখতে হবে, দ্যাট ইজ R2 প্লাস কে স্কোয়ার R1, তার মানে দ্য হোল থিং ইজ রেফার টু সেকেন্ডারি। অ্যান্ড যদি রিয়াক্টিভ ড্রপের বলে, তাহলে x2 প্লাস কে স্কোয়ার x1, তার মানে দ্য হোল থিং ইজ রেফার টু সেকেন্ডারি। এবার বলো, এটা কি বুঝতে পারা গেছে? শুধুমাত্র এই ফর্মুলাটা কিন্তু আমাদের লাগবে।
হ্যাঁ ম্যাম। ম্যাম
ও,
এখানে কি কেটা মানে কনস্ট্যান্ট টার্ম মানে কিছু
না
একটা?
না, কে আমাদের ট্রান্সফরমেশন রেশিও,
আচ্ছা,
আমরা পড়েছিলাম যে,
ট্রান্সফরমেশন রেশিও। আচ্ছা আচ্ছা।
এক্স্যাক্টলি আমরা ট্রান্সফরমেশন রেশিও পড়েছিলাম যে আগের ক্লাসে, দ্যাট ইজ
হ্যাঁ ম্যাম।
k equals to v2 by v1, or it will be n2 by n1, or it will be i1 by i2। তার মানে যদি আমি i1 বার করতে চাই, so i1 will be some other term of i2 into k, জাস্ট এটাই রিলেশন। ঠিক আছে, বোঝা গেছে?
হ্যাঁ ম্যাম।
ওকে, now this will be the case for refer to primary. Now if we convert it refer to secondary, then what we will do, that means x r1 will be there, and we have to transfer the secondary into primary. So we can write in this way, that is for the total resistive drop, if it is referred to primary side, then we can write it will be i1 r1 plus I1 R2 by k square. And if we take common I1, we can write R1 plus R2 by k square. This is the total resistive drop in the transformer, that is referred to primary. And for reactive drop, it will be I1 x1 plus I1 x2 by k square. Now why it is by k, I think you can do it in your own. Okay, that is we will get it from this expression. And if we take common I1, you can write x1 plus x2 by k square. So that is the referred to primary side, and we can mention this is our R01, this is our R, sorry, X01, as because this is the primary, and if we consider primary as 1, then the equivalent resistance and reactance, that is R1 plus R2 by k square and X1 plus X2 by k square, are the equivalent resistance and reactance that is referred to the primary. And if you further want to uh, draw the equivalent circuit that is referred to primary, so there we can write the R1 will be there, X1 will be there, that is the resistance and reactance of the primary, and the whole circuit will be referred to primary, that means the secondary will be referred to primary, and we can attach another one resistance and reactance with suppose the load, and this is my V1. So what will be the value of this resistance and reactance? So the value of this resistance and reactance will be R2 by k square. This is X2 by k square, and this is my load, and obviously then voltage will have some transformation ratio value, and this is our I1, that is none other than k into I2. So now we can say this circuit is the equivalent circuit of transformer referred to primary. Now similarly we can draw it for secondary circuit also. So the same expression will be same type of circuit will be there, and only the changes will be there. So if it is referred to secondary, that means we have to adjust our primary values according to that, and there we have already find out my primary side winding value will be, okay, that is, okay, just a minute. So this value will be, this value will be k square, R1, and this is my k square x1, and this is R2, this is x2, and this is the load. So this is V2 across this is my kV1, and the current is flowing, that is I2. So this is the equivalent circuit referred to secondary of the transformer. Now you can easily distinguish, that is, this is all the game of this K. So transformation ratio, and these are the two representation of equivalent circuit. If we think properly, we very easy to remember this thing. One is referred to primary, one is referred to secondary. যেটা আমি প্রাইমারিতে রেফার করছি তার মানে প্রাইমারি রেজিস্ট্যান্স ইজ অলরেডি দেয়ার, সাম another resistance we have to refer to primary, in terms of which connects the primary secondary, the transformation ratio. So primary secondary is transferred to primary. Now if we want to find out further for secondary circuit, so secondary resistance and reactance will be there only to convert the primary to secondary. Okay, so this is the case for equivalent resistance of primary to secondary. Acha, now this thing is clear to all of you.
Yes, ma'am.
Now, next point or next topic that we will discuss today is the voltage regulation. Okay, so before proceeding to voltage regulation, we will check that the syllabus, how much portion is there. Okay, so we are in module 3 and this is the magnetic materials, BH characteristic. We have studied ideal practical transformer, equivalent circuit. Okay, so that up to that much of portion we have completed. Now next will be losses in the transformer, regulation and efficiency. Okay, so voltage regulation is there. Now, what is voltage regulation? So voltage regulation is the way in which the secondary terminal voltage varies with the load depends upon which parameter, none other than the load current and the internal impedance and as well as the load power factor. So the change in secondary terminal voltage from no load to full load with primary voltage and frequency held constant is termed as the regulation. So, regulation determines the voltage characteristic of a transformer, and that's why it is termed as the voltage regulation. So, if we just want to define it, we can define in this manner that the change in the magnitude of secondary voltage when full load of specified power factor supplied at rated voltage is reduced to no load with the frequency and voltage held constant, it may be the percentage of rated terminal voltage. So we can write voltage regulation will be equal to E2 minus of V2 upon secondary rated voltage into 100. That is, if V2 is the secondary voltage, we know V2 is our secondary terminal voltage and E2 is our secondary voltage at no load. As because E2 is the EMF induced in the secondary, so the percentage regulation may be E2 minus V2 by secondary rated voltage into 100%. So also we can write that is E2 minus of V2 upon E2 into 100. That is the percentage regulation. Okay, now there will be two different term. One will be for zero regulation and another will be for the maximum regulation. So I will check if that much of extra portion is given in your syllabus. If it is there, I will tell it. Up till now, only know this thing, that is E2 minus V2 by secondary rated voltage into 100. Now, next, the important thing is the transformer losses. Now, we know what are the losses of the transformer. As transformer is a static type of machine, no rotating device is there. So, there is only two type of losses. One is iron loss, another is copper loss. So for iron loss is caused by the alternating flux that flows in the core, and iron loss is again two type. One is hysteresis and another is eddy current loss. Okay. Now, if the magnetic circuit is made up of iron and if the flux in the circuit is variable, so the current will be induced by induction in the iron circuit, and these currents are known as the eddy current. EDDY, eddy current. And eddy current result in loss of power, that is consequent beating for the material, and we know what are the two expressions for hysteresis loss and eddy current loss. That is, if I remember clearly, I have tell you the two relations of hysteresis and eddy current loss. Yes. So in this class, we have seen that is eddy current loss varies in the frequency f square, and hysteresis loss is proportional to the frequency, that is only f. Now, further if we just want to elaborate this thing, so we can also write that pH, that is eddy current loss, will be equals to eta max B max to the power x f v, some joules per second or watt. So what is f? F is the supply frequency. What is v? V, you can say the volume of core in cubic meter or meter cube, as we know that is what is the unit of volume. Now eta max, na eta dashed is the hysteresis coefficient, and B max is the peak flux density, and X value is lies between 1.5 to 2.5 depending upon the material, and generally the value is taken as 1.6. So this is the hysteresis loss, which is directly proportional with the frequency. And what about the eddy current loss? Eddy current loss is, say, some constant value is there. Now it will be B max square, F square, T square, V. Now B max, we know all of this, and F is the frequency, and V is the volume. So all this thing we know. And the flux in the circuit is variable, and current will be induced in the induction effect, and all these currents are the eddy current. So this is all about the losses or the iron losses. And what is there in the copper losses? Copper losses. These losses occur due to the ohmic resistance of the transformer winding. What are the two windings in the transformer? One is primary winding, another is secondary winding. And also we know what are the voltage drops and power losses in the windings. So ohmic loss or copper loss, if we have the I1 and I2 current are flowing in the primary and secondary winding, and if R1, R2 are the respective resistance of the primary and secondary winding, then copper losses will be I square R, that is I1 square R1 for primary winding, and it will be I2 square R2 for secondary winding. So the total copper losses will be this, that is I1 square R1 plus I2 square R2, and these losses vary accordingly. So these are all the losses about the transformer. So if anyone asks you about the transformer losses, or if the question will come in this manner: the losses in the transformer, option A iron loss, option B uh, winding, option B, suppose friction loss. Option C is no, option C is suppose another XYZ, and option D is all of this. So you have to choose the correct answer, that is iron loss and copper loss. So this kind of thing can come in your exam. Okay, now this is the losses that is included in your syllabus, and another will be the efficiency. Okay, now efficiency, in respect to the efficiency, transformer has a very high efficiency, as because the losses occurred in the transformer comparative to other machines is less. That means efficiency is equal to none other than output by input. Whatever the output is there and whatever we are giving the input, that is we can further write, so output divided by output plus losses. আমরা একটা ট্রান্সফরমারে ইনপুট দিচ্ছি, ধরে নে আমরা V1 সাপ্লাইটা দিলাম, ঠিক আছে, এরপর আমাদের কি হবে, আয়রন লস হবে, হিস্টেরিসিস লস, এডি কারেন্ট লস, সব লস হলো। আর আমাদের ওয়াইন্ডেজ লস হবে, এই যে প্রাইমারি ওয়াইন্ডিং এর মধ্যে I²1 R1, সেকেন্ডারি ওয়াইন্ডিং এর মধ্যে I²R2 লস হলো। তাহলে এই যে আয়রন লস আর কপার লস হলো, তার মানে কি এটা একটা লস হলো। তো তার মানে যে আমি আউটপুটটা পাচ্ছি, that output must be lesser than the input, as because output plus losses consist of this input. So further we can write, this is output by output plus iron losses plus copper losses. Okay, now again we can write 1 minus of Pi plus Pc upon output plus Pi plus Pc। দেখ তো আমরা লিখতে পারি, অবভিয়াসলি পারি। যদি আমরা এখান থেকে এটাকে মডিফাইড ইকুয়েশন লিখতে চাই, তাহলে পাওয়ার আউটপুট আমরা বলতেই পারি, আউটপুট পাওয়ার উইল বি V2 I2 cos phi, যেহেতু V2 is our terminal voltage secondary side, I2 is the current secondary current, and cos phi everyone knows this is power factor, and Pi equals to PH plus PE, and PC equals to I square R1 plus I2 square R2. So this is the transformer efficiency. Now the ordinary transformer has very efficiency, say for the range of 96 to 99%, and the difference between the readings of the output and input instrument is so small, and that's why the instrumental error will be also very small. And if the question come like this, that efficiency of a single phase transformer 30 to 40%, 50 to 60%, 70 to 80%, and 90 to 96% or 95 to 99%, you have to choose the correct answer correspondingly. So this is the efficiency of a transformer. Now another one term, please remember it, when we will get the maximum efficiency. So the condition for maximum efficiency, if copper loss Pc will be equals to Pi, that means if the iron loss will be equals to copper loss, then we will get the maximum efficiency of a transformer. Now the copper loss depend on current, iron loss depend on voltage, and total loss depends on this uh, volt ampere product. So that's why the transformers are rated in kVA, not in kilowatt. That thing is very very much important, that why the transformers are rated in kVA. In everywhere you can see that is the transformer rating will be given such as 100 AVA, 50 MVA. So this is termed in VA, that is volt ampere products. So copper loss depends on current. We can see that is I1 square, I2 square. So this is the case for copper loss. Iron loss depend on voltage. We know that is iron loss, whatever the amount of voltage we are giving, alternating voltage, and then the flux is there. So ultimately it will depend on the voltage, and the total loss in the transformer depends on this volt ampere product, not on this phase angle between the voltage and current. That means it is not dependent on the power factor. So that's why always transformers is rated in kVA. kVA. Okay, so this is all about the transformer, and this is also very important concept, that is whenever the copper loss will be equal to iron loss. If we apply our general knowledge, we can also conclude this term, that is if the copper loss will be equal to our iron loss, then we will get the maximum efficiency of a transformer. This is also a important concept for the short type of answer, that is if it is given to you, that is for 2 marks question obviously, when the transformer will give the maximum efficiency. Four options: copper loss greater than iron loss, copper loss equal to iron loss, copper loss less than iron loss, and none of the above. So you have to choose the correct answer. Okay, and this is all about the transformer for single phase transformer. Now, if it is also another term, that is all day efficiency. Now, all day means again there will be a term for energy. So, 24-hour will be considered in there, and energy means kilowatt hour. So, whatever we are getting the output in 24 hours, and whatever we are getting the input for 24 hours, so for that reason, the all day efficiency will be there. So that's it for today. And okay, so let me close the recording.